Okay, I know that I have talked about atomic number and atomic mass before, but just as a review because it relates to the last section of chapter 3. Atoms of different elements have different number of protons. This is atomic number, which is the number of protons of each atom, number of protons in the nucleus of each atom. Remember that the identity of the element is based on the atomic number. And of course, it's shown in the periodic table.
We first have got to understand the properties of the nucleus. Okay, this is pretty important, so pay attention here. The number of protons in an atom determines what element it is. 79 protons, always gold. 59 protons, always praseodymium. The number of protons in an element is its atomic number. It's right on top of the box in the periodic table because that is the element's defining trait. So an atom of silver with 47 protons in its nucleus is always an atom of silver. Depending on what its electrons are doing and what it's bonded to, it might be part of a chemical that's silver colored or black or blue or shiny or poisonous or a cure for disease. But whatever it is, that atom is still silver and will remain an atom of silver probably forever, because that core number is very, very difficult to change. Now, you might have known.
Okay, now we have isotopes. An isotope is an atom of the same element that have different masses. The different masses is based on the amount of neutrons. So we have hydrogen, deuterium, and tritium. Hydrogen has 1 proton, deuterium has 2, hydrogen has 1 proton, deuterium has 1 proton and 1 neutron, which gives it an atomic mass of 2, and tritium has a proton and 2 neutrons, which gives it an atomic mass of 3. So each of these have different atomic masses. However, because they all have 1 proton, they are all isotopes of hydrogen. This was one of the main things that Dalton got wrong in his original atomic theory, that he said that all atoms of the same element have the same size, mass, and properties. Then, of course, mass number is the total number of protons and the total number of neutrons in the nucleus of an isotope. Now, you might think, and this is the point of why I wanted to review this, is if lithium has 3 protons because its atomic number is 3, how can it have an atomic mass of 6.941? Because 6.941 would mean that there are 3.941 neutrons. If you take mass number minus atomic number, you get the number of neutrons. How can you have 0.941 neutrons? Well, the point is you can't, and that's why I wanted to, talk about how that relates to the average atomic mass. Okay, so because atoms are so small, scientists use a standard to control the units of atomic mass. That standard is carbon-12, which is one of the isotopes of carbon. Carbon-12 was randomly assigned a mass of exactly 12 atomic mass units, or AMU. 1 AMU is equal to 1/12 the mass of a carbon-12 atom. So the atomic mass of any atom is determined by comparing it with a mass of carbon-12. To be honest, we don't really use AMU in chemistry. It's just used as a basis to explain how we come up with the average atomic mass. The average atomic mass, this is why it's a decimal, is the weighted average of the atomic masses of the naturally occurring isotopes of an element. This is why your atomic masses on the periodic table are in decimal form, because they are averages. So, for example, if you have a box containing 2 different sizes of marbles, 25% of the marbles are 2 grams each, 75% of the marbles are 3 grams each. If you take 25 times 2, that's 50 grams. 75 times 3, that's 225 grams. Then you add those 2 together and divide by 100. The average marble mass is 2.75 grams. So there's 2 different ways to determine the average atomic mass. You can either do the one that I just showed you. So you take the percentage times the mass and you add those 2 together and then divide by 100. That gives you the average atomic mass. So with the marbles, you've got, again, 25 times 2 grams. So the total mass for all of the 2-gram marbles is 50 grams, and the total mass for all of the 3-gram marbles is 225 grams. So the total of all of the marbles in their percentages is 275. So you divide that by 100 and you get the average, which is 2.75. The method I prefer, which just makes it easier for me, which is to change the percent into a decimal. So you've got 2 grams times 0.25 plus 3 grams times 0.75 equals 2.75. That's 2 different methods, depending on whichever way that you're comfortable of getting the averages of the mass of substances. So how do we calculate the average atomic mass for elements? Let's use an example of copper. Copper, the naturally occurring isotopes of copper. 69.17% is copper 63 or Cu63, and that's equal to 62.929599 AMU, right? And this is what I mean when I say we use AMU as a basis to calculate average atomic mass. But once you just understand the principle behind what AMU is and that it was basically used as a standard to measure all of the other atomic masses, then we can forget about AMU. Okay, and then the other isotope of copper is copper 65, and that makes up 30.83% of all the naturally occurring isotopes, and that is 64.927793 AMU. So here's the percentages of each of the isotopes and what the mass of those isotopes are. So using method 2 from the slide before, we're going to change the percentages to decimals. So 69.17% becomes 0.6917. We're going to multiply that. Maybe I should actually use a pointer to help show. So we're going to take the 69.17% here, and we're going to change it to a decimal, multiply that times the mass of that isotope. We're going to add that to the decimal form of 30.83% times the atomic mass units for this isotope. And when you add them together, you get an average atomic mass of 63.55 AMU. The relative atomic mass scale makes it possible to know how many atoms of an element are present in a sample of that element with a measurable mass. There are 3 very important concepts that provide a basis for relating mass in grams to the number of atoms. And here's where we're going to start getting into how to calculate and how we calculate in chemistry. The first concept is something called the mole. Number 2 is Avogadro's number based on, I forget his first name, but Mr. Avogadro. And then the third concept is molar mass. So I'm going to go through those 3, and then I'm going to make separate videos for each of the types of problems that you'll come across, as well as upload a video about conversion factors and how we use them, because that's how we do calculations in chemistry, is using conversion factors to change from one unit to another. So I'm going to go through these concepts first. I'll upload this video, then I'll upload the video on conversion factors, and then I'll do practice problems for these kinds of questions. There's a whole lot of stuff coming at you this week. Okay, so the first concept is the mole, and it is not, in fact, that mole. The SI unit for an amount of substance is the mole. So if you learned about SI units, either from teacher Vanessa or maybe even in physics, SI stands for basically the French for international system. I think Système d'International. Anyway, so it's a standard system of units that we use for defining amounts of substances so that all the scientists all over the whole world are on the same page. So for example, for mass, the SI unit is a kilogram. And we do that because you've got scientists in different countries, and not every country uses the same system of units, particularly my home country of America, because we like to be different than everyone else. We're on the imperial system, so we use pounds and ounces and weird things, rather than a really easy metric system, which is based on an algorithmic thing. Anyway, so the mole is the unit for an amount of substance. Just like if we use the word 1 dozen specifies a specific amount, and that is 12. So the definition of a mole is the amount of substance that contains as many particles as there are atoms in exactly 12 grams of C12. So again, we're going back to using that standard of C12, and that 1/12, remember the 1 AMU is 1/12 the mass of C12. And now we're saying that a mole is the amount of substance that contains as many particles as there are atoms in exactly 12 grams of C12. Concept number 2 is going to define exactly how many particles that is for a mole. So Avogadro's number is the number of particles in exactly 1 mole of a pure substance, and that number specifically is 6.022 times 10 to the power 23. Yes, you have to remember that number. You'll be using that number for the next 2.5 years or 3 years. I think I teach science in semester 2 for grade 12 now. That's just a new thing that happened. 6.02 let me try that again. 6.022 times the power 10 to the power 23. So how big of a number is that? See if you can keep up with me here. If 5 billion people worked to count the atoms in 1 mole of an element, and if each person counted continuously at a rate of 1 atom per second, it would still take 4 million years to count all of the atoms in 1 mole. So think about every single second. 1001, 5 billion atoms. 1002, 10 billion atoms. 1003, 15 billion atoms. Doing that for 4 million years, then you would get to Avogadro's number. Finally, we have molar mass, and molar mass is the mass of 1 mole of a pure substance. It is written in a unit, gram per mole. So gram per mole or gram over mole, that is the unit for molar mass. It really is just grams per mole. How many grams are in 1 mole? Now, the nice thing about molar mass is that it's the same number as atomic mass. So if you go to, let me see if I got a periodic table here. Don't. Okay. Nothing. What do I have in here? I do. I just have to download the app real quick. Okay. All right, so periodic table. Okay, and if I click on, okay, so if you see, there we go. At the bottom, it says average atomic mass 63.545, and it says AMU there. That's also the same as gram per mole. I have to check to see if I've uploaded a periodic table for you yet. I don't know if I have. But anyway, so you find out in the periodic table, molar mass is the same as atomic mass. So for example, if you have a periodic table, you look at hydrogen, you look at the bottom number and it's 1.008. That represents 1.008 grams per mole. That's the molar mass of hydrogen.